All right, so you can see we jumped to chapter 6 for our notes here. So if you're referencing the textbook, I did put chapter 6 in there for Math Excel. We're still in Unit 3. Like I said, we have a couple more topics to cover before the test next Friday, and this is the normal distribution. So we know that from section 2.4, you'll recall we talked about the skewed distributions. We had like the left skewed, which was negatively skewed. We had the right skewed, which was positively skewed. And then we had that normal or bell-shaped curve, which was symmetric. So in that section, from that section, we know that an important aspect of the distribution of a variable is its shape. We can learn a lot about a random variable by looking at its shape. So the terminology of normal distributions, the larger the standard deviation, the flatter and more spread out the distribution. So normal distribution, and hence a normal curve, is completely determined by two things. It's the same things you used on Wednesday with the empirical rule. When you made that horizontal line and you marked something in the middle, what was it? The mean. And then when you counted out 1, 2, and 3 standard deviations. Standard deviations. So for a normally distributed variable, the percentage of all possible observations that lie within any specified range equals the corresponding area under its associated normal curve. Expressed as a percentage. So when discussing normal distributions of a variable, we are considering the entire population. So up until now, when we talked about the empirical rule, we were talking about the sample mean with x bar, right? That's what you wrote in the middle. And then lowercase s was the sample standard deviation. And that's what we used to count out from the mean. When we're talking about the population mean, we use a different symbol called mu. So it's like almost a mix between a U and an M. And we need a different symbol because it represents a different group, right? We've talked about when we try and find out information about a population, we often actually look at the sample, but this normal distribution is representing the entire population. So the symbol for population standard deviation is sigma. So you can kind of see it starts up, goes down and around. It's like when you first learn to write your name in cursive and then you write it all, everything, practicing your autograph. I was going to be an Olympic gymnast, so I practiced really hard on my autograph. No one ever asked. Maybe one day. I'm ready. So you can see a visual. I'm a visual person. The normal curves here represented by 3 different data sets. You can see this first one has a mean of -2, so it's centered at -2. And then the standard deviation is 1. That standard deviation is what tells us about the shape. So then when the mean changes, it just shifts along the x-axis to 3 in the center. But the standard deviation of 1/2 is what pushes that up and brings it in, because it's a smaller standard deviation, so there's less variation within the data points from that random variable. And then with the mean of 9, you can see again it bumped up, but it bumped up on the x-axis, but the standard deviation of 2 spread it out. Okay, because that data, because it has a standard deviation of 2, is more spread out. So then here's the question. How do we find areas under a normal curve? So the answer is we would need a table of areas for each normal curve. It's impossible. You can think of all of the potential data sets from all times past, present, and future. There's just no way to have a table of areas for all possible normal curves. So instead, the better answer is to have a standard normal distribution. Or standard normal curve would be a normally distributed variable having a mean of 0 and a standard deviation of 1. So we're going to learn to funnel each one of these distributions, each one of these normal curves, into this standard normal curve. Like standardized tests, you love those?
Oh, yeah.
Standardized tests you take so that we can make a comparison, like the ACT. So we know everyone in the country who's applying to Stanford has to get a 35 or whatever on their ACT. So that number is consistent. It means something consistent because everyone's taking the same standardized test. And that's kind of a comparison to what we're going to be doing. We'll be able to compare values better because we're going to standardize all of these different data sets. We're going to do a few examples, but first we'll take a look at a few properties. Property number 1, will you please read, Lainey?
The total area under the standard normal curve is 1.
Thanks. And that's key. And that's the one we'll reference most often in a specific way. So the area under the standard normal curve is 1. Keep that in mind. Gigi, read property 2, please.
The standard normal curve extends indefinitely in both directions, approaching but never touching the horizontal axis as it does so.
Great. So you'll notice it never touches. It's tempting to like make it touch and like close it off. It makes it look maybe neater, but it shouldn't ever touch. It's like an asymptote from Algebra 2 where the curve got closer and closer but never hit the asymptote. Property 3, will you read that one, Shelby?
The standard normal curve is symmetric about 0. That is, the part of the curve to the left of the dashed line in figure 6.8 is the mirror image of the part of the curve to the right of it.
So it's symmetric. Madeline, property 4?
Almost all of the area under the standard normal curve lies between 3 and 3, or negative 3 and 3. Sorry.
Good, and that should maybe bring up a reference to your lesson on Wednesday. Negative 3 and 3. You started at the mean and you went up 3 standard deviations and down 3 standard deviations from the mean, and that would encompass what percent of your data? 99.7, which is almost all. Okay, it's the same idea, but with a standardized variable or the standardized normal curve, we now are going from negative 3 to 3 instead of negative 3s to 3s. So here's the shift. We'll look at 3 different questions and sketch the normal distribution, then create the equation for the normally distributed variable x, and then calculate the z-scores. So when I say z-scores, I'm referencing this z right here. Okay, so the standardized variable follows this formula right here to help us create this normal curve, standard normal curve. So part A we'll do up here. Take your horizontal line, put your mean, this time it's mu instead of x bar, right in the middle there. And then we'll go up 1 standard deviation to 6, and down 1 to 0. Up 1 to 9, down another 1 to negative 3. And then up 1 to 12, and down another to negative 6. So we'll put a dashed vertical line up from mu of 3. And then you get to try and make this normal curve. Doing your best to make it symmetric and not hit the x-axis. So that's part A. Part B then is creating the equation for the standard, for the normally distributed variable x. So we'll write z equals, from that formula on the front, z equals x minus, it always starts that way, z equals x minus. We subtract the mean, so we'll subtract the mean of 3 and divide by the standard deviation, which also happens to be 3 in this example. And this is our equation. That's part B. Part C then says, hey, calculate the z-scores for the given x values. And I'm just going to have us calculate for some of these values in our normal curve. So we'll first start with calculating for m equals 3. Mu equals 3, sorry. So we're going to plug in a 3 for x, using 3 as one of our observations. So 3 minus 3 is 0, divided by 3 is still 0. So just below this normal curve, I'm going to create another one with the equivalent standard values. So we just converted 3 to its standard equivalent of 0. And we'll try 6. So z equals, we'll plug a 6 in for x, 6 minus 3 divided by 3. So that's going to give us 2. So, no, it's not. It's a 1. Thanks, Madeline. You're awake now. So that's a 1. Just seeing if you're awake, that's all.
Yeah.
I was just checking. Down to 0, so we'll do 0 minus 3 divided by 3. What is it? Never know when it's coming. It's -1. -1 goes down here. And we'll plug 9 in. Plug 9 in, 9 minus 3 divided by 3. Two. All right, so if we plugged in -3, any guesses on what would come out of the standard? -2. You guys catching on? Okay. Are you believers in the standardized variable yet? Okay, good. So that's how it works. So for any data set, so this is going to drive some of you nuts, I think. I'm going to overwrite on top of my work and make my normal curve here. There you go. Same thing, same normal curve, but now, and all normal curves would have the same shape, right? Area under the normal, all standard normal curves would be 1. So that's number 1. Number 2, I'm going to draw a horizontal line there, leave some space so you can put your numbers in. Mu in the middle is -2. Who can name off the 3 sigmas above the standard deviation, above the mean? So -2 up a half is going to be -1.5, then what? Yep. Then what? Yeah. There it is. And then down, 3. So what are we gonna, we'll land at -2.5, -3, and -3.5. Draw your dashed line, and then create your normal curve. So that's part A. Part B is when we write the equation. Z equals. It starts off Z equals X minus. But sometimes when we have a negative value like we do here for mu, so we'll have X minus -2, which then would be written as plus. So it'll be X plus 2 divided by 1/2. And we could calculate our values again, so we could plug in a -2 in the numerator, and we would get -2 plus 2 is 0. It would land here, right? We would end up with the same values if we plug each of these values into our z-score formula here. Question 3, go ahead and try that on your own.